Okay, so in this video we are going to be looking at the preparation of hydrogen. Okay, the preparation of hydrogen, and this is just a part one of the preparations of hydrogen. Okay, so feel free to pause this video and copy if you want the things that are outlined for you here, and then I will be running you through these same things and perhaps even explaining something much more in detail and something much more in depth. Okay, so like I have written for you, a hydrogen may be prepared either in the laboratory or in the industry. Okay, hydrogen may be prepared either in the laboratory or in the industry. So in this whole video I'm just going to be talking about the laboratory preparation of hydrogen. Okay, the laboratory preparation of hydrogen. Anytime you hear the word preparation, the word preparation just means to produce or to manufacture. So if I say preparation of hydrogen, I'm just talking about the production of hydrogen or the manufacturing of hydrogen. And like we have said, that might be done either in the laboratory or in the industry. Okay, now anytime hydrogen is being prepared in the laboratory, we can prepare it in the laboratory using two pathways. One, by reacting a metal with water, okay, or secondly, by reacting a metal with an acid. These are the two best examples which I can give you, and these are some reactions which are very, very much common even in the exam. Okay, so firstly, by reacting a metal with water, and secondly, by reacting a metal with an acid. Okay, so here, under reacting a metal with water, you're going to see me react sodium. So Na is what we call sodium, and sodium is reacting with water in this case, and our products here are sodium hydroxide and hydrogen gas. Okay, again, if you see this second example, we're seeing magnesium being reacted with water, and we're having magnesium hydroxide with hydrogen gas. Thirdly, you're going to see that when aluminium is reacted with water, we are seeing aluminium hydroxide being produced with hydrogen gas. So what is happening here is that there is like a partial displacement reaction that is taking place, in the sense that it is not all the hydrogen atoms of the water molecules that we have that are being replaced by these metals. So sodium is in group 1, magnesium is in group 2, aluminium is in group 3, and this is more like the general reaction of metals, in the sense that anytime metals react with water, they always produce a hydroxide with a hydrogen gas. So that's the first way, by reacting a metal with water. So sodium plus water, we're going to have sodium hydroxide. Magnesium with water, we're going to have magnesium hydroxide. Aluminium, upon being reacted with water, we're also seeing aluminium hydroxide being produced. And the hydrogen gas, which we're interested in, is also being produced at the end of the reaction. There is partial displacement that is taking place here, in the sense that it's not all the hydrogen atoms of the water molecules that are being replaced by these metallic atoms or metallic ions at some point. Okay, so I encourage you to also look up on how these chemical formulas are being made. I always encourage people to say that writing correct chemical formulas is important, especially if you are to balance up your chemical equation correctly. So if you notice, the way sodium hydroxide is appearing and the way magnesium hydroxide is appearing and the way aluminium hydroxide is also appearing are very, very different. Sodium is in group 1. The hydroxide is a radical and it also has a valency of 1. Sodium is in group 1, so its valency is 1. The hydroxide also has a valency of 1. So because they are um, because they are having the same valency, they're equivalent. It's just the same as just putting all these things together. There won't be any um, much of a change that is going to be there. But if you look at magnesium hydroxide that we have here, the magnesium is in group 2, the hydroxide has a valency of 1, and because the magnesium is in group 2, its valency is also 2, and because of that, the 2 on the magnesium has just been transferred to the hydroxide here, and the 1 on the hydroxide has just been transferred on the magnesium. To show you briefly, it's just like us having magnesium having a valence of 2. The hydroxide has a valency of 1. So if the values swap here, you're going to see that the 1 on the hydroxide will come on the magnesium, and the 2 on the magnesium will just go on the hydroxide, and that's what we're going to have. It also happened with the sodium. Sodium had a valency of 1. The hydroxide also had a valency of 1. So it's just like these two values, the two numbers just swapped, and usually we do not show the ones, so that's the reason why sodium hydroxide is just appearing in that way. Aluminium is in group 3 on the other hand, and aluminium has a valency of 3 because it is in group 3. The hydroxide has a valency of 1, so the 1 is going to come on the aluminium, and then the 3 is going to go on the hydroxide, and this is what we have. And please be sure to put your brackets there, very, very important. So that's just what I can say further a little bit on reacting a metal with water as one of the ways in which hydrogen can be produced in the laboratory. Secondly, we can produce hydrogen by reacting a metal with an acid. So again, I have just written the 3 metals, the sodium, the magnesium, and the aluminium, because they are in different groups, and I just wanted to show things differently. The HCl that you see here is hydrochloric acid. This HNO3 here, that's what we're going to be calling as nitric acid, and this is sulfuric acid. Now, the difference between the first reaction and the second reaction is that in this one, when we react a metal with an acid, there will be a full displacement that is going to be taking place. In the first reaction, there was a partial displacement that was taking place, in the sense that it is not all the hydrogen atoms of the water molecule that were replaced by the metal, but in this one, you're going to see that there will be a full displacement that is going to be taking place. Sodium is very much more reactive than hydrogen, so the sodium is going to displace the hydrogen from its position, and hence we're going to have sodium chloride with the hydrogen gas that has been displaced here. Sodium is going to displace the hydrogen, and we're going to have sodium chloride plus the hydrogen gas there. A displacement reaction is a reaction in which a more reactive metal displaces a less reactive metal. Displacement reactions again can also be assigned to nonmetals, in the sense that you can also say that displacement reactions are reactions in which a more reactive nonmetal displaces a less reactive nonmetal. And of course, that will be explained when we talk about the reactions of the group 7 elements. But for now, let us just stick to metals. So sodium is displacing hydrogen in order for us to have sodium chloride with the hydrogen gas that has been displaced. Sodium has a valency of 1. The chlorine as well has a valency of 1. So we're just going to write it up in the same way as we did for the sodium hydroxide, because they're equivalent. Magnesium is going to react with nitric acid. So HNO3 is nitric acid. And nitric acid here, the hydrogen that it has is going to be displaced by the magnesium, because the magnesium is more reactive than hydrogen. So when magnesium displaces hydrogen from its position, what we're going to have is magnesium nitrate plus the hydrogen gas. Again, I'm encouraging you to be aware of valencies. Magnesium has a valency of 2, like we have seen. The nitrate is a radical which has a valency of 1. So if we swap the two numbers here, the one on the nitrate is just going to come on the magnesium, and the 2 which is on the magnesium is just going to go on the nitrate. And hence what we're going to have is this formula for magnesium nitrate plus the hydrogen gas. There isn't any hydrogen atom present here, which means that there is a full displacement that is taking place, like I have explained. And then lastly, in this reaction, we're seeing aluminium being reacted with sulfuric acid. So H2SO4 is what we're going to be calling as sulfuric acid. When aluminium reacts with sulfuric acid, again, a full displacement reaction is going to take place, in the sense that all the hydrogen atoms of this acid, or all the hydrogen ions of this acid, are going to be replaced by the metal right here. So how is it going? If we look at it, when aluminium reacts with sulfuric acid, what we're having is aluminium sulfate. So the Cl is called the chloride. The NO3 is the nitrate. The SO4 is what we're going to be calling as the sulfate. So when the aluminium displaces the hydrogens, what we're going to have is aluminium sulfate. And this is how the chemical formula of aluminium sulfate is supposed to be written. Why? Because aluminium has the valency of 3, as we have said, and the sulfate is a radical, which has a valency of 2. And if we swap the two values, the 2 on the sulfate is going to come on the aluminium, and the 3 on the aluminium is going to go on the sulfate. Hence, what we're going to have is this chemical formula for the aluminium sulfate, and of course, we're also going to see hydrogen gas being produced. So this is one of the ways, these are one of the ways in which you can produce hydrogen, in which you can prepare or manufacture hydrogen in the laboratory by reacting a metal with water, and also by reacting a metal with an acid. When we react a metal with water, there is partial displacement that is taking place, in the sense that it's not all the hydrogen atoms of the water molecule that are going to be replaced by the metal. That's why you're going to see hydrogen atoms still being present, because there is partial displacement that is taking place. But if you react a metal with an acid, there is full displacement that is taking place here, in the sense that all the hydrogen ions of this acid, of these acids, are being reacted or are being replaced by these metallic atoms that we have. So anytime a metal reacts with water, we always have a hydroxide and hydrogen gas produced at the end of the day. Whether it's a group 1 metal, a group 2 metal, or a group 3 metal, we always have a hydroxide and hydrogen gas produced at the end of the reaction. Anytime a metal reacts with an acid, we always have a salt and hydrogen gas produced at the end of the reaction. Whether we are having a group 1 metal, a group 2 metal, or a group 3 metal, it's all general. We always have a salt and hydrogen gas which are produced at the end of the reaction. And the salts, in this case, are sodium chloride, magnesium nitrate, and aluminium sulfate, alongside the hydrogen gas that has been liberated due to a full displacement reaction that is taking place. And of course, it's just important that I at least show you some interesting facts about hydrogen as we just sum up everything. Well, one thing that you need to know is that this hydrogen is highly flammable. It is extremely flammable. It is able to react, can I say, explosively with oxygen gas at some point. It is very, very flammable, and it is for this reason why we can't use hydrogen in hot air balloons, because you might just end up burning yourself. It is highly flammable, okay? Highly, highly flammable, okay? Apart from that, you need to understand that hydrogen has about 3 isotopes associated with it. And anytime you're talking about isotopes, isotopes are just atoms of the same element having the same atomic number but different mass numbers. Or, if you want, you can say that isotopes are atoms of the same element having the same atomic number but different neutron numbers. So, in your definition of isotopes, you can either include mass numbers or neutron numbers. But one thing that you must not leave out is you stating that they are atoms of the same element having the same atomic number. So 3 isotopes of hydrogen, there is what we call protium, which can also be called hydrogen 1. There is deuterium, which is hydrogen 2. There is tritium, which is hydrogen 3. So protium is the normal hydrogen that we usually write, and which is, of course, commonly found on many periodic tables. So protium is hydrogen 1, is the normal hydrogen. Deuterium is hydrogen 2. Tritium is hydrogen 3. Okay? And these ones, I think I'll come and explain much more better in detail about this. They are usually involved in some certain reactions in physics, which we call nuclear fusion reactions. And anytime these isotopes of hydrogen undergo nuclear fusion reactions, there is a vast amount of nuclear energy that is just released together with some helium atoms or helium nuclei that are also released along the way. So these ones are much more explained in depth when you're talking about what we call nuclear fusion reactions. So this is what I can say about the 3 main isotopes of hydrogen: the protium, the deuterium, and the tritium. And lastly, one thing that you need to know is that hydrogen gas has both metallic and non-metallic properties. It's for this reason why you're going to see hydrogen being placed at the top center of the periodic table, because it has both metallic and non-metallic properties. So hydrogen has no specific group because of this same statement that I've just written here. But just because it has no specific group doesn't mean that it doesn't have a specific period that it is found on. So hydrogen does not have a specific group, but it is in period 1 of the periodic table. It has no specific group because it has both metallic and non-metallic properties. So this is what we can say for now. And this is just a summary for the laboratory preparation of hydrogen. And these are just some interesting facts about it. So I hope this helps.